I do two things. I design mobile computers and I study brains. And today's talk is about brains. And yay, I got a brain fan out there. I'm gonna, if I can have my first slide up here, and you'll see the title of my talk and my two affiliations. So what I'm going to talk about is why we don't have a good brain theory, why it is important that we should develop one, and what we can do about it. And I'll try to do all that in 20 minutes. I have two affiliations. Most of you know me from my Palm and Handspring days. But I also run a nonprofit scientific research institute called the Redwood Neuroscience Institute in Menlo Park. And we study theoretical neuroscience, and we study how the neocortex works. And I'm going to talk all about that. I have one slide on my other life, the computer life, and that's this slide here. These are some of the products I've worked on over the last 20 years. Starting back from the very original laptop, from the first tablet computers and so on, ending up most recently with the Treo. And we're continuing to do this. And I've done this because I really believe that mobile computing is the future of personal computing, and I'm trying to make the world a little bit better by working on these things. But this was, I have to admit, all an accident. I really didn't want to do any of these products, and very early in my career, I decided I was not going to be in the computer industry. And before I tell you about that, I just have to tell you this one little picture of graffiti there. I picked off the web the other day. I was looking for a picture of graffiti, the little text input language, and I found a website dedicated to teachers who want to make these, the script writing things across the top of their blackboard, and they had added graffiti to it, and I'm sorry about that. So what happened was when I was young and got out of engineering school at Cornell in '79, I decided I went to work for Intel, and I was in the computer industry. And 3 months into that, I fell in love with something else. And I said, I made the wrong career choice here. And I fell in love with brains. This is not a real brain. This is a picture of one, a line drawing. But, and I don't remember exactly how it happened, but I have one recollection which was pretty strong in my mind. In September of 1979, Scientific American came out with a single topic issue about the brain. And it was quite good. It was one of the best issues ever. And they talked about the neuron and development and disease and vision and all the things that you might want to know about brains. It was really quite impressive. And one might have the impression that we really knew a lot about brains. But the last article in that issue was written by Francis Crick of DNA fame. Today is, I think, the 50th anniversary of discovery of DNA. And he wrote a story basically saying, well, this is all well and good, but you know what? We don't know diddly squat about brains, and no one has a clue how these things work, so don't believe what anyone tells you. This is a quote from that article. He says, what is conspicuously lacking, he's a very proper British gentleman, so what is conspicuously lacking is a broad framework of ideas in which to interpret these different approaches. I thought the word framework was great. He didn't say we didn't even have a theory. He says we don't even know how to begin to think about it. We don't even have a framework. We are in the pre-paradigm days, if you want to use Thomas Kuhn. And so I fell in love and said, look, we have all this knowledge about brains. How hard can it be? And is this something we could work on in my lifetime? I felt I could make a difference. And so I tried to get out of the computer business into the brain business. First, I went to MIT. The AI lab was there. And I said, well, I want to build intelligent machines too. But the way I want to do is to study how brains work first. And they said, oh, you don't need to do that. We're just going to program computers. That's all we need to do. I said, no, you really ought to study brains. They said, no, you're wrong. And I said, no, you're wrong. And I didn't get in. But I was a little disappointed, pretty young. But I went back again a few years later, and this time I was in California, and I went to Berkeley. And I said, I'll go in from the biological side. So I got in a PhD program in biophysics. And I was, all right, I'm studying brains now. And I said, well, I want to study theory. And they said, oh, no, you can't study theory about brains. That's not something you do, and you can't get funded for that, and as a graduate student, you can't do that. So I said, oh my gosh, I was very depressed. I said, but I can make a difference in this field. So what I did is I went back in the computer industry, and I said, well, I'll have to work here for a while, do something. That's when I designed all those computer products. And I said, I want to do this for 4 years, make some money. It's like I was having a family, and I would mature a bit, and maybe the business of neuroscience would mature a bit. Well, it took longer than 4 years. It's been about 16 years. But I'm doing it now, and I'm going to tell you about it. So why should we have a good brain theory? Well, there's lots of reasons people do science. One is, the most basic one, is people like to know things. We're curious, and we just go out and get knowledge. Why do we study ants? Well, it's interesting. Maybe we'll learn something really useful about it, but it's interesting and fascinating. But sometimes a science has some other attributes which makes it really interesting. Sometimes a science will tell something about ourselves. It'll tell us who we are. Rarely, evolution did this, and Copernicus did this, where we have a new understanding of who we are. And after all, we are our brains. My brain is talking to your brain. Our bodies are hanging along for the ride, but my brain's talking to your brain. And if we want to understand who we are and how we feel and perceive, we really understand what brains are. Another thing is sometimes science leads to really big societal benefits, technologies or businesses or whatever that come out of it. And this is one too, because when we understand how brains work, we're going to be able to build intelligent machines. And I think that's actually a good thing on the whole, and it's going to have tremendous benefits to society. It's just like a fundamental technology. So why don't we have a good theory of brains? And people have been working on it for 100 years. Well, let's first take a look at what normal science looks like. This is normal science. Normal science is a nice balance between theory and experimentalist. And so the theorist guys say, well, I think this is what's going on, and the experimentalist says, no, you're wrong, and it goes back and forth. You know, this works in physics, this works in geology. But if this is normal science, what does neuroscience look like? This is what neuroscience looks like. We have this mountain of data, which is anatomy, physiology, and behavior. You can't imagine how much detail we know about brains. There were 28,000 people who went to the neuroscience conference this year, and every one of them is doing research in brains. A lot of data. But there's no theory. There's a little wimpy box on top there, and theory has not played a role in any sort of grand way in the neurosciences. And it's a real shame. Now, why has this come about? If you ask neuroscientists, why is this the state of affairs? They'll admit it. But if you ask them, they say, well, there's various reasons we don't have a good brain theory. Some people say, well, we just don't have enough data. We need to get more information. There's all these things we don't know. Well, I just told you there's so much data coming out your ears. We have so much information we don't even know how to begin to organize it. What good is more going to do? Maybe we'll be lucky and discover some magic thing, but I don't think so. This is actually a symptom of the fact that we just don't have a theory. We don't need more data. We need a good theory about it. Another one is sometimes people say, well, brains are so complex. It'll take another 50 years. I even think Chris said something like this yesterday. I'm not sure what you said, Chris, but something like, well, it's one of the most complicated things in the universe. Well, that's not true. You're more complicated than your brain. You've got a brain. And it's also, although the brain looks very complicated, things look complicated until you understand them. That's always been the case. And so, we can say, well, my neocortex, which is the part of the brain I'm interested in, has 30 billion cells. But you know what? It's very, very regular. In fact, it looks like it's the same thing repeated over and over and over again. It's not as complex as it looks. That's not the issue. Some people say brains can't understand brains. Very Zen-like. Whoa. You know, it sounds good, but why? I mean, what's the point? It's just a bunch of cells. You understand your liver, it's got a lot of cells in it too, right? So, you know, what? I don't think there's anything to that. And then finally some people say, well, you know, I don't feel like a bunch of cells. You know, I'm conscious, I got this experience, I'm in the world, and, you know, I can't be just a bunch of cells. Well, you know, people used to believe that there was a life force to be living, and we now know that's really not true at all. And there's really no evidence this is all, other than people just have disbelief that cells could do what they do. And so some people have fallen into the pit of metaphysical dualism, some really smart people too, but we can reject all that. No, I'm going to tell you there's something else, and it's really fundamental, and this is what it is. There's another reason why we don't have a good brain theory, and it's because we have an intuitive, strongly held, but incorrect assumption that has prevented us from seeing the answer. There's something we believe that just is obvious, but it's wrong. Now, there's a history of this in science, and so before I tell you what it is, I'm going to tell you a bit about the history of it in science. You look at some other scientific revolutions. In this case, I'm talking about the solar system, that's Copernicus, Darwin's evolution, and tectonic plates, that's Wegener. And they all have a lot in common with brain science. First of all, they had a lot of unexplained data, a lot of it. But it got more manageable once they had a theory. The best minds were stumped. Really, really smart people. We are not smarter now than they were then. It just turns out it's really hard to think of things, but once you've thought of them, it's kind of easy to understand it. My daughters understood these three theories in their basic framework by the time they were in kindergarten. And you know, it's not that hard. You know, here's the apple, here's the orange, you know, here's the earth goes around, that kind of stuff. Finally, another thing is the answer was there all along, but we kind of ignored it because of this obvious thing. And that's the thing. There was an intuitive, strongly held belief that was wrong. In the case of the solar system, the idea that the earth is spinning, and the surface of the earth is going like 1,000 miles an hour, and the earth is going through the solar system at about 1,000,000 miles an hour, this is lunacy. We all know the earth isn't moving. Do you feel like you're moving 1,000 miles an hour? Of course not. You know, and someone who said, well, we're spinning around in space and it's so huge, they would lock you up, and that's what they did back then. So, you know, it was intuitive and obvious. Now, what about evolution? Evolution is the same thing. We taught our kids, well, the Bible says, you know, God created all these species. Cats are cats, dogs are dogs, people are people, plants are plants. They don't change. Noah put them on the ark in that order, blah, blah, blah. And, you know, the fact is, if you believe in evolution, we all have a common ancestor. And we all have a common ancestor with the plant and the lobby. This is what evolution tells us. And it's true. It's kind of unbelievable. And the same thing about tectonic plates. You know, all the mountains and the continents are kind of floating around on top of the earth, you know? It's like, doesn't make any sense. So, what is the intuitive but incorrect assumption that has kept us from understanding brains? Now, I'm going to tell it to you, and it's going to seem obvious that it's correct, and that's the point, right? Then I'm going to have to make an argument why you're incorrect about the other assumption. The intuitive but obvious thing is that somehow intelligence is defined by behavior. That we are intelligent because of the way we do things and the way we behave intelligently. And I'm going to tell you that's wrong. What it is intelligence is defined by prediction. And I'm going to work you through this in a few slides here. I'll give you examples of what this means. Here's a system. Engineers like to look at systems like this. Scientists like to look at systems like this. They say, well, we have a thing in the box, and we have its inputs and its outputs. The AI people said, well, the thing in the box is a programmable computer, because that's equivalent to a brain, and we'll feed it some inputs, and we'll get it to do something, have some behavior. And Alan Turing defined the Turing test, which is essentially saying, we'll know if something's intelligent if it behaves identical to a human. A behavioral metric of what intelligence is. And this is stuck in our minds for a long period of time. Reality, though, I call it real intelligence. Real intelligence is built on something else. We experience the world through a sequence of patterns. And we store them, and we recall them. And when we recall them, we match them up against reality, and we are making predictions all the time. It's an internal metric. There's an internal metric about us sort of saying, do we understand the world? Am I making predictions? And so on. You're all being intelligent right now, but you're not doing anything. Maybe you're scratching yourself or picking your nose, I don't know. But you're not doing anything right now, but you're being intelligent. You're understanding what I'm saying. Because you're intelligent and you speak English, you know what word is at the end of this sentence. The word came into you. You're making these predictions all the time. And then what I'm saying is that the internal prediction is the output of the neocortex. And that somehow prediction leads to intelligent behavior. And here's how that happens. Let's start with a non-intelligent brain. Well, I'll argue a non-intelligent brain. We're going to call it an old brain. And we're going to say it's like a non-mammal, like a reptile. So let's say an alligator. We have an alligator. And the alligator has some very sophisticated senses. It's got good eyes and ears and touch senses and so on, a mouth and nose. It has very complex behavior. It can run and hide. It has fears and emotions. It can eat you. You know, it can attack. It can and do all kinds of stuff. But we don't consider the alligator very intelligent. It's not like in a human sort of way. But it has all this complex behavior already. Now in evolution, what happened? First thing happened in evolution with mammals, we started to develop a thing called the neocortex. And I'm going to represent the neocortex here, but this box that's sticking on top of the old brain. Neocortex means new layer. It is a new layer on top of your brain. If you don't know this, it's a wrinkly thing on the top of your head that just got wrinkly because it got shoved in there and it doesn't fit. Literally, that's what it is. It's about the size of a table napkin and it doesn't fit, so it gets all wrinkly. Now, look at how I've drawn this here. The old brain is still there. You still have that alligator brain. You do. It's your emotional brain. It's all those things and all those gut reactions you have. And on top of it, we have this memory system called the neocortex. And the memory system is sitting over the sensory part of the brain. And so as the sensory input comes in and feeds through the old brain, it also goes up into the neocortex. And the neocortex is just memorizing it. It's sitting there saying, I'm going to memorize all the things that are going on, where I've been, people I've seen, things I've heard, and so on. And in the future, when it sees something similar to that again, so in a similar environment or the exact same environment, it'll play it back. It'll start playing it back. Oh, I've been here before, and when you've been here before, this happened next. And it allows you to predict the future. It allows you to, it feeds back the signals into your brain. They'll let you see what's going to happen next. Will let you hear the word sentence before I said it. And it's just feeding back into the old brain that allows let you make very more intelligent decisions. This is the most important slide of my talk, so I'll dwell on it a little bit. And so all the time you're saying, oh, I can predict the things. So if you're a rat and you go through a maze, and then you learn the maze, the next time you're in the maze, you have the same behavior. But all of a sudden you're smarter because you say, oh, I recognize this maze. I know which way to go. I've been here before. I can envision the future. And that's what it's doing. In humans, by the way, this is true for all mammals. It's showed up in mammals. In humans, it got a lot worse. In humans, we actually developed the front part of the neocortex called the anterior part of the neocortex. And nature did a little trick. It copied the posterior part, the back part, which is sensory, and put it on the front part. And humans uniquely have the same mechanism on the front, but we use it for motor control. So we are now able to make very sophisticated motor planning and things like that. I don't have time to get into all this, but if you want to understand how a brain works, you have to understand how the first part of the mammalian neocortex works, how it is we store patterns and make predictions. So let me give you a few examples of predictions. I already said the word sentence. In music, if you've heard a song before, if you heard Jill sing those songs before, when she sings them, the next note pops into your head already. You anticipate it as you're going. And if it was an album of music, at the end of one album, the next song pops in your head. These things happening all the time. You're making these predictions. I have this thing called the altered door thought experiment. And the altered dark thought experiment says you have a door at home. And when you're here, I'm changing it. I got a guy back at your house right now moving the door around, and they're going to take your doorknob and move it over 2 inches. And when you go home tonight, you're going to put your hand out there, and you're going to reach for the doorknob, and you're going to notice it's in the wrong spot. And you go, whoa, something happened. It may take a second to figure out what it was, but something happened. Now, I could change your doorknob in other ways. I can make it larger or smaller. I can change it from brass to silver. I can make it a lever. I can change your door. I can put colors on it. I can put windows in it. I can change 1,000 things about your door. And in the 2 seconds you take to open your door, you're going to notice that something has changed. Now, the engineering approach to this, the AI approach to this, is to build a door database. It has all the door attributes. And as you go up to the door, let's check them off one at a time. Door, color. We don't do that. Your brain doesn't do that. What your brain is doing is it's making constant predictions all the time of what is going to happen in your environment. As I put my hand on this table, I expect to feel it stop. When I walk, every step, if I missed it by 1/8 of an inch, I'll know something has changed. You're constantly making predictions about your environment. I'll talk about vision here briefly. This is a picture of a woman, and when you look at people, your eyes saccade over it 2 to 3 times a second. You're not aware of this, but your eyes are always moving. And so when you look at someone's face, you typically go from eye to eye to eye to nose to mouth. Now, when your eye moved from eye to eye, if there was something else there, like a nose, you'd see a nose where an eye's supposed to be. And you go, holy shit, There's something wrong about this person. And that's because you're making a prediction. It's not like you just look over there and say, what am I seeing now? A nose, that's okay. No, you have an expectation what you're going to see every single moment. And finally, let's think about how we test intelligence. We test it by prediction. What is the next word in this? This is to this, is this is to this. What is the next number in this sentence? Here's three visions of an object. What's the fourth one? That's how we test it. It's all about prediction. So what is the recipe for brain theory? First of all, you have to have the right framework. And the framework is a memory framework, not a computational or behavior framework. It's a memory framework. How do you store and call these sequences of patterns? Spatial temporal patterns. Then, within that framework, you take a bunch of theoreticians. Now, biologists generally are not good theoreticians. That's not always true, but in general, there's not a good history of theory in biology. So I found the best people to work with are physicists, engineers, and mathematicians who tend to think algorithmically. Then they have to learn the anatomy, and they've got to learn the physiology. You have to make these theories very realistic in anatomical terms. Anyone who gets up and tells you their theory about the brain works and doesn't tell you exactly how it's working in the brain and how the wiring works in the brain isn't not a theory. And that's what we're doing at the Redwood Neuroscience Institute. I would love to have more time to tell you we are making fantastic progress in this thing. And I expect to be back up on the stage maybe this one, maybe some other time, in not too distant future, and tell you about it. I'm really, really excited. This is not going to take 50 years at all. So what will the brain theory look like? First of all, it's going to be a theory about memory. Not like computer memory. It's not at all like computer memory. It's very, very different. And it's a memory of these very high-dimensional patterns, like the things that come from your eyes. It's also a memory of sequences. You cannot learn or recall anything outside of a sequence. A song must be heard in sequence over time, and you must play it back in sequence over time. And these sequences are auto-associative recall, so if I see something or I hear something, it reminds me of it, and then it plays back automatically. It's an automatic playback. And prediction of future inputs is the desired output. And as I said, the theory must be biologically accurate, it must be testable, and you must be able to build it. If you don't build it, you don't understand it. So I'm going to tell you one more slide here. What's this going to result in? Are we going to really build intelligent machines? Absolutely. And it's going to be different than people think. No doubt that this is going to happen in my mind. First of all, it's going to be built up. We're going to build this stuff out of silicon. The same techniques we use for building silicon computer memories we can use for here, but they're very different types of memories. And we're going to attach these memories to sensors. And the sensors will experience real-world data. And these things are going to learn about their environment. Now, it's very unlikely the first things you're going to see are like robots. Not that robots aren't useful and people can build robots, but the robotics part is the hardest part. That's the old brain. That's really hard. The new brain is actually kind of easier than the old brain. So the first things we're going to do are the things that don't require a lot of robotics. So you're not going to see 3CPO. You're going to more see things like intelligent cars that really understand what traffic is and what driving is, and have learned that certain types of cars with their blinkers on for half a minute probably aren't going to turn, things like that. We can also do intelligent security systems. Anywhere we're basically using our brain but not doing a lot of mechanics. Those are the things that are going to happen first. But ultimately, the world's the limit here. I don't know how this is going to turn out. I know a lot of people who invented the microprocessor. And if you talk to them, they knew what they were doing was really significant. But they didn't really know what was going to happen. They couldn't anticipate cell phones and the internet and all this kind of stuff. They just knew, like, hey, we'll do calculators and traffic light controllers. But it's going to be big. In the same way, this is like a brain science, and these memories are going to be a very fundamental technology, and it's going to lead to very unbelievable changes in the next 100 years. And I'm most excited about how we're going to use them in science. So I think that's all of my time. I'm over, and I'm going to end my talk right there.